Good day. I'm going to discuss building construction. So our module 1 is that has something to do with the introduction to building construction. In structural engineering terms, a building can be considered as a series of individual interconnected components whose function is to transfer externally applied loads through a structural system into the building's foundations. So what is architectural structures? The aim of this module is to enable the students of architecture to develop an intuitive understanding of structural engineering so that in the long term they are able to conduct productive dialogues with structural engineers. So what is structure? So structure is the load carrying part of all natural and man-made forms. It is the part which enables them to stand under their own weight and under the worst conditions of externally applied force. The designer, in the context of structure, a designer is one who conceives a structural part or a structural system which functions satisfactorily, is integrated successfully within the overall design, and is appropriate for its purpose in terms of material and form. The design process. Without a brief, it is not possible to design, since there are no rules and no constraints. Therefore, no matter how sketchy, it is the brief which sets the basic framework for the designer. It provides the lead in for the first analysis of the problem, which then develops into an iterative process with ideas being tested, modified, rejected until an appropriate solution to the problem is reached. Optimum design. A designer should be generally aim for the optimum solution in order to obtain the maximum benefit with the minimum use of material within the constraints of strength, stiffness, and stability. The result will be efficiency, combined ideally with elegance and economy. So here, the brief glossary of the terms used in structural engineering. So force is a measure of the interaction between two bodies measured in newtons or kilonewtons. Load is a force acting on a structural element measured in newtons or kilonewtons. So mass is a measure of the amount of materials in an object measured in kilograms, or abbreviated as kg. Sigma, mathematical term meaning the sum of. So for example, this is the total sum, cos 2 of the forces, cos 2 F1 plus F2 plus F3. Weight, a measure of the amount of gravitational force acting on an object, measured in newtons or kilonewtons, where 1 kilonewton is equivalent to 1000 newton. Force is an influence on a body producing or tending to produce change in shape or movement. So number one is Newton's first law of motion. So the physical law that the body remains at rest or in motion with a constant velocity unless an external force acts on the body, also called law of inertia. Newton's second law of motion, the physical law, that the sum of the forces acting on a body is equal to the product of the mass of the body and the acceleration produced by the force with motion in the direction of the resultant of the forces. And number three is the Newton's third law of motion. So the physical law that for every force acting on a body, the body exerts a force having equal magnitude and opposite direction along the same line of action as the original force. So also called law of action and reaction. So structure, sometime constructed, especially a building or part, synonymous to building. External loads, when external or dead load or wind load are applied to a building, they induce external forces within the structural elements that are transmitted into and resisted by the foundation. So we have external loads can be applied to a structural member in two fundamentally different ways. Actually, these loads act in the direction parallel to the length of a member and typically induce either internal compression or tensile forces within it. So we could see here that these actually loads are actually found in figure letter A. So this represents that it is in compression, while if the arrow is pointing outward, the column or the structural member, it is in tension. And number two, perpendicular or shearing. Loads act perpendicularly to the direction of the length of a member, depending on the geometry of the member and point of application of the load. So we are actually referring to set B and set C. So this is actually an example of a beam. So this could also serve as the diagonal member. So it may be a truss or it may be a stairs. So we can even presume that this one is the stairs itself. So each of the 5 internal forces induced by externally applied load, tension, compression, shear, bending, and torsion. So these are the basic relationship between loads and structural elements under figure 1. Letter A. So letter A coincides with principal axis, axial internal forces, which is actually depicted here on letter A. And for letter B, load perpendicular to the principal axis, bending type internal force. So once again, let us have a quick look at it. And then letter C, the load inclined to the principal axis, combined axial and bending type internal force. So kindly refer to figure C. While this second figure, the tensile form, is now known to be the active shape because it has no rigidity. A cable must take up a shape, the form active shape, which allows it to resist the load with a purely tensile internal force. We have different loads arrangement produced. So the different form is now what we call the active shape. While for the third figure, we have here the compressive form or active shape once again, but it is in a reverse manner. So what is axial? Axial loads act in the direction parallel to the length of a member. They can either act to resist compression loads, which try to shorten a member, to resist tensile loads, which try to lengthen the member. Members in structural system that are under compression loads are termed struts, or if they are vertical, they are called columns. Members under tensile loads are termed ties. Shear. The internal shear force acts perpendicularly to the direction of the length of a member and are induced by externally applied shear loads. For the purposes of analysis, shear loads are considered to be applied to a structural member via either point loads, such as a person standing on a beam, or distributed loads, such as the weight of a floor supported by a beam. Bending is also termed flexure, occurs when a load is applied perpendicularly to the longitudinal axis of a member. This load induces internal forces that act parallel to the length of a member. The magnitude of these internal forces varies proportionally across the depth of the member from compression at one's phase to tension at the other. At the point between the compression and tension phases, the internal force is zero. This is termed the neutral axis. The algebraic sum of the internal forces multiplied by the distance from the neutral axis is called the bending moment. So moment normally occurs simultaneously with shear forces and are measured in kilonewton meters, or abbreviated as capital letter K, N, and small letter M. A simple example of a bending load moment can be demonstrated via vertical shear load applied to the end of a cantilevering beam. In this situation, the bending moment can be calculated as the applied shear load multiplied by the length of the cantilever. So torsion, if the point of application of the load is eccentric from the longitudinal axis of the member, a twisting moment will be developed. This in turn induces torsional force within the member to resist the twisting action. Torsionally forces are distributed across the cross-section of a member in a circular manner where the outer fibers experience Dias forces. The magnitude of torsion is a product of the applied load and distance from the point of application to the longitudinal axis of the member. Torsion is measured in kilonewton meters, or abbreviated as capital letter K, N, and small letter M. Let us tackle the Newton's third law of motion. So Newton's third law of motion states that forces occurs in pairs, with each force of the pair being equal in magnitude and opposite in direction to the others. Hence, a building to be stable, every external load or force that is applied to it has to be resisted by an equal and opposite force at the supports. This state is called static equilibrium. Categories of structures. This section considers structures as whole entities of interconnected components and examines how they can be categorized and stabilized. Heinrich Engels developed a system of categorization for structures, which was first published in 1965. He separated structural types into four categories. One is form active, second is vector active, third is surface active, and fourth is section active. These categories form a useful system for examining the primary structural drivers for the vast majority of structural forms. Engels categories provide designers with a useful framework within which structural forms can be grouped. Once that the mechanism of load transfer in a building is identified, a designer can determine what parameters will and will not affect the structural efficiency of that building and develop a design accordingly. In reality, the practical requirement of achieving the required building function, form, and aesthetic while supporting irregular loading conditions often determine that structural components will have to be designed to act in more than one mechanism of load transfer at any one time. For example, a floor plate may be designed to support vertical loads via a section active mechanism and simultaneous distribute lateral load to structural cores via a surface active mechanism. Similarly, arches and trusses are commonly required to support irregular loads that induce bending stress in their components, thus reducing their structural effectiveness in effect. Most buildings are designed to compromise to some extent between pure structural efficiency and practical requirements. Form active. Form active structures rely on a series of flexible, non-rigid components to achieve a stable form under loading. The most simplistic and easily apparent of these forms is a chain or rope bridge, which will deflect in order to reflect the position of any load placed upon it. Other, more three-dimensional examples include the tensile fabric and the grid shell structures, which when placed under tension also create stable forms that can be manipulated using double curves to create more interesting and more stable arrangements. So this is actually an example for the form active shape. So take note, it is a form active shape. It is an example of a grid shell structure. This figure 4, the grandstand at Lord's Cricket Ground found in London. The year is 1987. It was designed by Michael Hopkins and partners. They are architects, and together with their structural engineers, Ove Arup and partners. The canopies which form the roof of this building are form active tensile membranes. While this another example is the pneumatic structures, or further examples of structures whose form is directly related to the hydrostatic forces applied to them. Another example of form-active structure. So this is found in Burton, Maloo, Silverdome. A very large span is achieved here with a cable, reinforced air, supported membrane, which is a tensile form active structure. More common, but less obvious example of form active structures includes the arches. An arch can be considered to act in a similar manner to a loaded chain, with the exception that whereas the chain's component are in pure tension, an arch component are in a pure compression. Or you could simply visualize an egg, that an egg of a chicken is in pure compression. In a perfectly efficient form active structure, the components are subjected to pure axial stresses, either compression or tension only. If a point load is applied to the surface of a flexible form active structure, deformations will occur. Even rigid arches will develop bending under point loads unless the load is applied vertically at the crown of the arch, which significantly reduces their structural efficiency. So example of form active structures. Number one is we have the Olympianhalle Olympic Park, Munich, Germany. It was built in 1972. It's a tensile fabric structure. Second is the Seville building, a grid shell structure. Visitor Center at Windsor, Great Park, UK. It was designed by Glenn Howells Architects and engineered by Buru Appold and Robert Haskin in the year 2006. Third example of form active structure is the work of Antoni Gaudi, the Casamile. Number 4 is the traditional stone arch of a Roman aqueduct found in Segovia, Spain, or simply the fifth and final example of form active structure is a suspension bridge. Form active, we are already done with it. Let us proceed to vector active. Vector active is structural forms transfer loads via a series of interlinked rigid components which are small in comparison to the length of the overall structure and therefore not capable of developing significant bending or shear forces. The distribution of the externally applied force back to the points of support is subject to the directional and geometrical relationships between the components. Hence, the term vector active is simply two-dimensional truss. It's the most common example of a vector active structure. More complex examples include space frames and spherical or hemispherical dome structure. So we have the sports dome, Perth, Scotland. This laminated timber built up section can be produced in a variety of configurations in addition to straight beams. Here is a series of arch elements is used to produce the framework of a dome. So we are actually tackling here the vector active form. The efficiency of a vector active structure is dependent on the individual members working in axial and compression only, rather than in bending. To achieve this, load must be applied at or through the point where the members connect, known as nodes. In reality, it is often impossible to avoid some bending moment occurring in some members of a truss due to accidental loading scenarios, or in the case of bridges, due to the load of traffic on the bottom part. Therefore, individual components of vector active structures are often designed with some additional sectional capacity to avoid instabilities developing. So example of vector active structures. Number one is the Cape Fear Memorial Truss Bridge found in Wilmington, USA. Second is the Lamella Dome of the Palazzetto dello Sport, Rome, Italy, designed by Pier Luigi Nervi, and the space frame structure. Now, let us discuss the surface active form. So surface active structure include concrete of masonry domes, cellular building, and concrete shell. These are characterized by rigid surfaces that are capable of developing axial, compression, and tension, and shear stresses. As with form active structures, any applied forces are redirected via the form or shape of the structure, and therefore shape is intrinsically linked to structural performance. The efficiency of a surface active structure is dependent on the form of the surface in relation to the forces applied to it. For example, the efficiency of a dome is driven by its height in relation to its span. A perfectly hemispherical dome is the most structurally efficient form in terms of material used and volume encapsulated. So this is another example of the surface active form structure, which is the exhibition hall of the CNIT, found in Paris, France. The architect here is Nicolas Esquilin. So the principal element of a self-supporting reinforced concrete shell. Again, as with form active surfaces, surface active structures are poor at supporting point loads that generate local bending stresses. Opening within a stress surface or other discontinuities also reduce the structural efficiency of the system. When a surface active structure is designed purely to respond to the forces applied to it, it can be extremely efficient form. For example, the reinforced concrete roof, the Sydney Opera House of Australia. In many buildings, the floor structure is designed as a horizontal surface active structural element. These are known to be a diaphragm. This is used to transfer lateral loads into the vertically stiff elements of the buildings, such as the shear walls or lift cars. Example of surface active structures, the Sydney Opera House of Australia, designed by John Hudson. And the second example is the Villa Savoye, found in Poissy, France, by Le Corbusier. Section active structures are the most versatile and most common form of structure in Engel's system. Section active structures rely on the sectional properties of individual rigid components, such as beams and columns, to support applied loads. All buildings that are constructed from beams, slabs, and columns, from agricultural sheds to high-rise commercial buildings, can be described as section active. In contrast to form and vector active systems, the components of a section active system are designed to resist bending, shear, and torsion forces, as well as axial tension and compression. This is an example of a section active structure. You could see here the structural members, its bracing, and its component. Either it is a steel frame or reinforced concrete. So here we have a typical bracing seam for a multi-story framework, vertical plane. Bracing is provided in a limited number of bays and positioned symmetrically on plan. All other bays are linked to this by diagonal bracing in the horizontal plane at every story level. The structural efficiency of a section active structure is dependent on the cross-sectional properties of the individual components and their unrestrained length and height. Example of section active structures. Number one is the standard concrete structural frame. Number two, standard steel structural frame. And number three is standard timber structural frame. So this ends my lesson.